to say on both the previous occasions I've overrun a little.
It's not a bother.
The caretaker's not going to throw us out.
Shane, do you want to mute us all?
Everyone should be muted, yeah.
Okay. If I go to screen share, I'll start off with my slideshow. So can everyone see that?
Yes.
Yep. Okay. Wonderful. Okay. So the Megaconstellation threat. As Alan said, we've at the RAS there's been a panel. In fact, the first meeting was on the 31st of January, and I only found out about this threat only slightly before that. And the meeting on the 31st of January was between principally professional astronomers, and I think myself and Brian Sheen from the Roseland Observatory were the only two amateurs in the room. I count myself as an amateur, even though I've got a degree in astrophysics from centuries ago, and so I've done the stuff, but I consider myself more of an amateur and organizing amateurs rather than as a professional astronomer. So without further ado, we have my first page. Don't worry, the other transitions aren't as slow and messy as that one. Megaconstellations, I'm going to ask what they are, and then go on to talk later in the talk about what threat they are to astronomy from different points of view, different types of observation and different types of observer. But not only am I going to talk about the threat to astronomy, but also they're a threat to the way that we can safely and sustainably use space, as in launching things into orbit, launching things further out to go out to the moon, the planets and beyond. And then there are also some legal and political considerations with the megaconstellations that I will touch on at the end. So the first thing is, what is a megaconstellation? Well, the initial thing was a constellation of satellites is a dozen or a few dozen small satellites, and a megaconstellation is just perhaps several thousand satellites, maybe even many hundreds and several thousands of satellites. The first satellite was launched back in October 1957, Sputnik 1. And it's been estimated that there have been over 8,000 launches since then, with nearly 2,000 or thereabouts satellites still active. That's not counting, of course, all of the other junk that's up there with discarded boosters and fairings that have shrouded satellites, and then you remove the fairing and the satellite is released. And then there's the odd nut and bolt and spanner and things like that, as well as flakes of paint floating around up there. But in terms of active satellites, about 2,000 or so. Now, way back in the days, shortly after Sputnik 1, launching a satellite was very, very expensive. If you were going to launch for example, a typical communications satellite, which was 6 to 8 tons worth up into a high orbit, then it was going to be around $100 to $400 million. Now, that's the kind of money that only governments and large corporations could afford. And on top of that, you've got the ongoing costs for tracking and monitoring and license fees for the use of the radio bands and all of those things as well. So the costs were pretty big. Over time, electronics has become smaller and more efficient. And the ability now to create small satellites with miniaturized electronics means that it is now a lot cheaper to launch a satellite. So that a CubeSat, for example, which is about 4 inches by 4 inches by 4 inches, is about 20,000 or so to launch. And if you wanted to build a bigger CubeSat, which is basically by assembling several of the 4 by 4 by 4 inch cubes together, you'll find that a larger one may still only cost you $500,000 or something like that. So in practice, the cost of small satellites has come down tremendously. And partly because of that, you can launch lots of them, not just the odd 1 or 2 from a single launcher. So that brings the launch cost per satellite down as well. So because you can launch a lot of them, that's what They do. They launch a whole group of them at the same time, and hence the constellations. And with the arrival of SpaceX and Elon Musk actually owning the company that does the launching as well as the company that makes the satellites, his per launch costs are even lower because you haven't got to pay someone else to launch your satellites. So the rise of the mega constellations. So what type of orbits do you put satellites into? So working from the bottom here of the table upwards, you have the low Earth orbits or near Earth orbits. And traditionally that means anything with an altitude of less than 2,000 kilometers. That's an altitude above the Earth's surface, not distance from the center, of course. So there is also another category, which I haven't shown here, which is often referred to as VLEO, which is very low Earth orbit. And that means satellites may be orbiting at 300 to 500 kilometers, something like that. Then you get the medium Earth orbit satellites. And the medium Earth orbit satellites typically will have orbital periods of around 12 hours or something like that. They're often in elliptic orbits. A 12-hour orbit relative to the Earth means that it passes over the same place twice in a day. Not used a lot, as you can see by the numbers up the side, 132 here compared to the others. After that, you've got the geosynchronous and geostationary orbits. The geostationary orbit is an orbit at a specific altitude of 35,780 kilometers, because at that altitude, the satellite will orbit the Earth excuse me, in 24 hours, meaning that it stays above the same longitude if the orbit is circular. A geostationary orbit is also in the same plane as the Earth's equator. Now, it's the geostationary orbit slots, the positions that are available in this circular ring around the Earth. It's those particular places that are most prized, because if you think about your sky satellite dish, you haven't got to steer it to follow a satellite across the sky. Your sky satellite is always in the same place in the sky. The difference between geostationary and geosynchronous is that if the orbit is inclined to the Earth's equator, or if the orbit is slightly elliptical, then you will have the projection, the position on Earth's surface above which the satellite is passing, trace out a long figure of 8. The up and down motion is because the orbit is inclined, and the figure of 8 is because sometimes the satellite's angular rate going around the Earth in its orbit is in advance of the Earth's rotation rate. And sometimes when the satellite is further out at apogee or near apogee, it falls behind the Earth's rotation rate. So when you take that into consideration with the up and down motion because of the inclination, you get a long figure of 8. That's a very useful orbit to use for things like communication satellites. Sometimes things have been launched up into the higher Earth orbits, but they're much less frequently used. The thing about the geosynchronous and geostationary orbits is that you can put one big satellite out there, 6 to 8 tons, as I say, wasn't unusual, with a big dish, big solar panels, and very powerful transmitters, because it has to transmit all the way down to the Earth's surface. And from there, the satellite can see about 40% of the Earth's surface. So if you use only a few of those around the Earth, talking to each other as well as up and down to the ground, then you can pretty much cover the whole globe. Maybe some areas near the poles are not quite so easy to get out. Not many people live there. And as we'll see, one of the advantages of the Megaconstellation satellites, the small ones in low Earth orbits, is that they don't need as much power because they're lower down, but they only see a smaller spot size on the ground. In particular, two types of orbit that I wanted to mention. One of them here is the Molniya orbit, which is at a very specific inclination of 63.4 degrees, because at 63.4 degrees, with typically a 12-hour period, you find that the satellites will stay in the state with the same angle all the time. It'll cross over the same direction relative to the ascending node all the time, because the precession of the orbit it disappears. It's mathematically, you can work out that the bulge of the Earth and other factors mean that it rotates around with the Earth. So it's a very good orbit to use, and has the other big advantage that this long elliptical orbit means that the satellite spends a lot of time high up looking down at perhaps a point in the northern hemisphere, and then very quickly zips around down the southern hemisphere and back up again, and spends again a fair amount of time looking at the northern hemisphere. So if you want to put a spy satellite up, that is a very good type of orbit to use, because you spend more time spying on the Americans or the Russians or the Chinese or whoever you're after. The other type of orbit that is most relevant to what my talk tonight is this one, the Walker configuration. Now, the Walker configuration, you can see from these orange lines, in fact, what it is, it's a whole set of circular orbits around the Earth, but there are lots of them, all staggered in the point where they cross the equator. So it forms this kind of mesh weave of satellites around the Earth. And you can see also from this that near the top of the orbit here, you can see that there is apparently what looks like an increased density of the orbit. That's merely because the satellite, when it reaches the apex of its orbit on the northern hemisphere, slows down the rate at which it traverses the latitudes before it turns southwards again. And so the density of satellites here is higher than the density down near the equator. And I can demonstrate that later on. So the big advantage is, yes, you've got now all of the ability to launch these small, relatively cheap satellites. If you can put them into a low Earth orbit, you need lots of them, because satellite, which is at 550 kilometers, by contrast with the big communication satellites, can only see about 4% of the Earth's surface. So it's just as well they're cheap, because you have to have a lot of them if you're going to get global coverage. The other big advantage is that the communication satellites out at 35,786 kilometers have quite a considerable round trip delay, simply because of the radio signal out to them and the radio signal coming back, the distance it has to travel. So you could well be looking at several milliseconds, perhaps 40 or 50 milliseconds or something like that, for a round trip time out to a communication satellite in geosynchronous orbit. That's not really a problem if all you're doing is streaming a Netflix movie or something like that. But if you're a keen gamer, computer gamer, for example, before you've even managed to wiggle your joystick, you've been shot. And so really, one of the one of the advantages of the low Earth orbit satellites is that you can have a much shorter time to travel for the signal out and back, where maybe it's down. I think Elon Musk recently said his early tests show 10 or slightly over 10 milliseconds, which is very good. One of the other factors to consider is these satellites will ultimately be equipped with laser transmitters and receivers, so that not only will they be beaming up and down to the ground, but they also be talking to each other using laser. So if you send a communication message up to one of the satellites, it will then beam it using laser to other satellites until eventually it reaches a point where it needs to beam the signal down to the Earth again. And the advantage of that compared to a ground optical cable is that the speed of light in a vacuum is higher than the speed of light in glass. So by the time you've added up on the ground the length of optic fiber plus the various optical repeaters and relays and things like that on the route, you've actually got quite a significant delay compared to the broadcast of a signal up to the satellite and then the transmission of a light beam across a vacuum to other satellites and then down to the ground again. And it turns out that there is also a significant advantage of using low Earth orbit satellites compared to sending the signal through an optic fiber network. So what sort of mega constellations are going to be put up there? It's in the nature of, first of all, articles that you write, and particularly where they're published, like the FAS newsletter, and also even with these talks, it's you have to work hard to keep them up to date. So I don't guarantee that the numbers in this table are 100% up to date, but you can see here that SpaceX are planning quite a large network of satellites, and they are, at the moment, they are the company that is most advanced in their ambitions to launch satellites. And I'll come on and talk about SpaceX in more detail for the rest of the talk. In fact, most of the talk will be based around what SpaceX are doing. You have companies like Amazon who want to put up some 3,000 or so satellites, and other companies, Samsung. There has been some talk that Facebook wants to put satellites up there. It may be that they will decide that it's not somewhere they really want to go, or maybe they're just sitting back waiting to see what others do first, rather than break new ground. Facebook don't have the infrastructure to put their own satellites up there yet, so maybe they're looking to see how the market develops first. The other company that's been in the news recently is OneWeb, and in fact, I'm in a meeting tomorrow as part of this Mega Constellation panel of the RS. In a meeting tomorrow with OneWeb to talk to them. OneWeb is a UK company, and it applied to launch 700 and something satellites. And then it had problems. It ran into problems with their investors, and they filed for Chapter 11 bankruptcy in the US. That just means that their creditors can't make them insolvent prematurely. It gives them the chance to reorganize their company, reorganize the structure under strict oversight from the regulators. And provided the regulators are happy with the reorganization, then they will allow them to continue trading. And in this case, OneWeb managed to get themselves bought by a consortium of the UK government, who have, I think, about a 45% stake, and Bharti Global Limited, which is an Indian company. While they were in Chapter 11 bankruptcy, they filed an application with the FCC, this is the American Federal Communication Commission, to launch 48,000 satellites in total, just over 48,000. I don't know whether they still have the plans to launch that many. I'll probably find out tomorrow. But I know that their plans have changed a little, for example, on the altitude of the satellites that they're planning to use. Even if you exclude OneWeb and Facebook and Link, which is one of the others, you have 58,600 satellites. And if you have OneWeb do launch the 48,000, you're talking about 100,000 satellites, which is obviously clearly way, way more than the 8,000 or so launches that have been made and the couple of thousand satellites that are currently still up in orbit. So there is a concern about how visible will these satellites be and what sort of threat do they pose, given how many of them are going to be up there. Okay, So if I go on to the SpaceX now and talk more specifically about SpaceX, I've divided SpaceX's ambitions into 3 phases. There's the initial ones. In fact, phase 1, in fact, even comes in 2 parts. SpaceX are rushing to get the first 1,584 53 degrees, this second line here, because they claim that that is the minimum required to give them some internet coverage. They can do proof of principle, and at that point they can start to sign up subscribers and things like that. They're already about halfway on the way to doing that, with over 700 launched already. The FCC is involved because the FCC provides the licenses giving them permission to launch. The FCC needs to know what frequency bands they're going to use and gives them permission to use them. And also it has to make sure that their plans for the launch make sensible use, that in the way that the satellites are going to be deorbited afterwards and various things like that. So basically making sure that their use of the radio spectrum and their plans for the satellites in orbit are reasonable, including things too like precautions on collision avoidance and safety in terms of the satellites not blowing up and creating debris. But I'll come on to that later on. But the FCC, traditionally, the FCC have said you have, I think it's 6 years from the point when they grant the license up to when the satellites have to be in orbit, and making use of the spectrum that they've been allocated. Otherwise, they lose the right to use that spectrum. With Megaconstellations and so many thousands, they've taken a slightly different view that you have to have half of them by a certain time and the remainder within another period of time. So what they've done here with the phase 1 is they said that half of the 4,408 have to be launched by 29th of March 2024. So we can expect to see at least a couple of thousand of them up there by 2024. And all of that first phase must be launched by 29th of March 2027. There's also a second phase that they want to launch. And they have a slightly later deadline for November of 2024 and November of 2027. So clearly a lot of satellites, that's 12,000 satellites that they've currently been given permission to launch, and they've got until 2027 to do so. We're talking therefore about 7 years from now, and they've already got 700 of them up there out of the 12,000. So I suspect unless there are any major problems for them, they will achieve the 12,000 satellites that they want to get up there. They did apply, however, for what I've labeled here as phase 3, which is another 30,000 satellites. And if you look at the numbers here, where we've got, for example, at 53 degrees, there's another 3,000 satellites there at 53 degrees, and another 4,500 here at 53 degrees. And the reason why I'm highlighting 53 degrees, of course, is because the UK is typically between about 50 and 54 degrees, 55 degrees, something like that, which means that the upper apex of their orbit is going to be passing straight over places like Manchester. And my comment earlier on about the Walker configuration, about the fact that they seem so much more concentrated at the top, at the apex of their orbit, means that the density of these satellites over our skies in at least the southern UK is going to be quite high. And I've got a table, a chart to show you on the next slide. So this 30,000 satellites, as they hasn't been approved yet. And there is quite a lot of work going on to try and make sure they don't get approval for the other 30,000. And also to try and make sure that OneWeb don't get approval for their ambitions of 48,000. Again, we may not be successful in that. SpaceX have got fingers in lots of pies. They're the entrepreneurial golden boys, and I think my guess is that they're going to get away with the 30,000 as well. So this chart, this graph, is actually updated from the one that I put into my article in the FAS newsletter. So what does it show? If we consider just the phase 1 and phase 2 satellites, it shows how many satellites will you see per 100 square degrees if you look up towards the zenith. This is not how many can you see, sorry, this is how many will there be in a 100 square degree area. So it's 10 degrees by 10 degrees. Just to give you a feel for what that is, the square of Pegasus is 207 square degrees. The bowl of the Ursa Major's Dipper is 43.7 square degrees. And if you count the rough quadrangles above and below the belt of Orion, add those together, then that's about 81 square degrees. So that gives you a feel for what 100 square degrees is. So this shows that if you're looking, for example, at around the 53-degree orbit area where we are, where they were passing over us, you can see that typically you could have up to 0.4 of a satellite per square degree, per 100 square degrees, which doesn't sound like very much, but that means a lot of them in the sky, and they are moving, of course. So you're going to have them coming through your nominal square of 100 square degrees on a regular basis. If the phase 3 satellites get added as well, then those numbers go up considerably. As I say, this is not necessarily how many you will see, because it depends on things like the illumination by sunlight. This is how many are actually going to be there. If you're looking at the satellites, oops, let's go back, sorry. If you're looking at the satellites in the infrared, of course, the satellite may start out being illuminated by sunlight, and as it moves into the shadow, the warm satellite will still be glowing in the infrared. And if you are an amateur radio astronomer, of course, illumination by sunlight is not the thing that makes them visible for you. It is the fact that they are belting out radio waves down towards the Earth. And there's more to that I'll come to later on. Okay, so the satellites themselves, the early ones were the Starlink 0.9 versions. They were a little bit lighter, and they only used one particular frequency band, and about 5% of them was estimated to be survivable down to the ground. The later satellites have now got other things added to them, as well as a visor that has been added. And they are also being redesigned to be 100% destroyed on re-entry. Something that's common to both of them is they have a cylinder of krypton gas on board. That krypton gas is ionized and accelerated out through a nozzle, so that you have a relatively low mass of gas being ejected at very high speed, which gives you a very small thrust. And that small thrust is used fairly continuously to keep the satellite in orbit, and also to accelerate deorbit when the satellite's life comes to an end. There are the antenna underneath the satellite is a phased array, and a phased array means that you can actually steer where the beam is. In fact, you can actually have multiple beams and steer them in different places, which is quite good for perhaps avoiding certain areas on the ground or targeting specific areas on the ground. It's got a single solar panel of about 1 by 9 meters, and it has a star tracker system to align itself accurately. The satellite is also provided with data from the US Department of Defense, so that it can also autonomously avoid satellites that it may be getting too close to. Having said that, there was an issue just after the launch where one of the satellites, one of ESA's satellites needed to be moved. I'll come on to that later. So, given that the satellites have a small footprint on Earth, you've got to have a lot of them, and also you need to have lots of ground stations on the ground with a ground antenna about the size of a pizza box pointing up to the ground. And SpaceX have designed the ground antenna and software for picking up the signal to be as easy as possible. Pretty much, they say, as plug in and go. And they've applied for a license of up to 1 million ground stations in the US alone, and they're going to have to apply for ground stations in other countries as well before the satellites can be used there. Initially, these satellites are being launched 60 at a time. There have been a couple of launches where they've launched fewer than that because they've launched some other satellites as well as the Starlink satellites. And when eventually the new Starship is completed, Gwynne Shotwell, who is the SpaceX president, has said that they will be able to launch 400 at a time. And I'll come on to later on reasons why, in fact, 400 at a time from their point of view, 400 at a time will be necessary. Okay, so as I say, one of the things is that it's a requirement for the filings to the FCC that the satellites should avoid each other. And so they have this onboard system, which is led by the Combined Space Operations Center, which is the US-led organization. And so they keep SpaceX and their satellites fully up to date with everything that potentially could be a threat, a collision threat. Because a collision out in orbit can be quite significant. A small 1 kilometer CubeSat at 7 kilometers per second has the energy of about 6 kilograms of TNT. So you can imagine that if a CubeSat of that mass collides with another satellite, it's going to do a lot of damage. And similarly, these Starlink satellites are bigger than that, and therefore would be likely to have more impact than that. And there are going to be a lot of them. So there has to be a tremendous amount of effort involved in making sure that these satellites cannot collide with others. It doesn't actually say what happens if something goes wrong and you can't steer your satellite anymore, if it goes dead for you for some reason. They do try and do testing of the satellites. In fact, the initial launch of all of these satellites is going to be into a 290 kilometer high orbit. And then once in that orbit, they will test the satellite's electronics, check that they can communicate with it, to check that they can command it and so on. And they check it out in that low orbit. Part of the reason for that is if the satellite turns out to be a dud, then at that altitude, it's still in the very outer fringes of the Earth's atmosphere. And within a week or two, the satellite should automatically spiral inwards and re-enter. So the reason for this low 290 kilometer orbit is literally as a safety measure for satellites that aren't working. They didn't survive the launch. When they're launched into that particular orbit, they are in an open design where the solar panels are parallel to the body of the satellite, and the visor is also parallel to the body of the satellite. So it's like a flat sheet. The reason for that is that you actually don't want to present too much of a drag surface straight away, because it may be that your satellite is fine, but your thrusters are going to have to be working overtime to overcome the amount of drag at 290 kilometers altitude. So you orient the satellite edge on in the direction of travel so that it doesn't get dragged too much. Once the satellite's been tested out, they then move it into what they call the shark configuration, which is where the solar panels are upright, as in vertical compared to the Earth, where the satellite body is parallel to the Earth's surface, so that the transmitters and things can point down to the Earth's surface. And then the visor staff, the visor, is a smaller panel on the opposite edge to the solar panel, and that's at right angles, and it's designed to shade the underside of the satellite from sunlight. And I'll come on to that a bit more later. So there's a lot of rubbish up there. You can see that ESA takes the numerical approach to how big things are, bigger than 10 centimeters, whereas NASA say bigger than a softball. They have slightly different estimates of sizes, but overall you can see that there are many thousands of pieces of things up there, and a worryingly large number of items. Even if you took an average here of some 25,000 items bigger than 10 centimeters, that's still a lot of rubbish up there orbiting the Earth that could present a threat. And of course, most of that doesn't have thrusters and can't be controlled. So it's important that the Starlink satellites, in fact all satellites, are able to maneuver their way around this debris. Stuff that's at 10 centimeters or bigger can be tracked by ground, so you can avoid the larger debris. It's the smaller stuff, the stuff that's a millimeter in size, that is harder, well, can't be tracked and is harder to avoid. Even something that is a millimeter in size, traveling at those high velocities, could cause a significant amount of damage. You could punch a hole in your solar panel, for example. Could puncture your krypton gas cylinder, maybe. Depends on the angle that it hits the satellite. And even small things like flecks of paint can be quite dangerous. The thing is, once you get something that's maybe a millimeter or two across, hit a satellite, even if it's a metal body area of a satellite, it causes little craters, and it causes vaporization of the metal where a small particle hits. And you then add to the number of droplets of metal, little globules of things floating around in orbit. So there is a gradual erosion of satellites over time because of very small particles that are in orbit. So anything you do that increases the number of those small particles seriously has to be avoided. And if you don't do that, it may be that space will gradually become non-usable. You also need to make sure that your satellites aren't going to explode. Your batteries, you have to have a battery. Your satellite clearly will work fine when the solar panels are in sunlight, but when you go into the shadow of the Earth, you have to have a battery to provide power. Those batteries must be safe. They can't explode or catch fire. Electronic components have got to be thoroughly tested to make sure that they don't burst into flames or explode. Capacitors, for example, can't explode. They've all got to be solid state capacitors, and they've all got to be thoroughly tested and space vetted, if you like. And then things too, like the krypton gas cylinder, you have to make sure that it is thoroughly shielded so that a micrometeoroid impact, for example, doesn't cause the satellite to explode. So SpaceX have had to provide plans on all of those sorts of things. And in particular, they've had to talk about how they plan to deorbit their satellites when they get to the end of their life. They've said that if you have a satellite in a 550-kilometer orbit, it will deorbit by itself within 5 years. 550 kilometers is low enough down that the atmospheric drag, even though very tenuous at that altitude, is still enough to cause the satellite to spiral in if it can't work at all anymore. You can't command it to maintain its position. When it gets to the end of its lifetime, and typically these satellites have got a 5 to 7 year lifetime, the plan is that you use the remaining fuel. You have to reserve some fuel to do this, but you use some of the remaining fuel to lower perigee. So these satellites are going to be in a very circular orbit. It's a case that when you've got any satellite that's orbiting in a slightly draggy environment, that the orbits will circularize. So you deliberately need to decircularize that. So you fire your thrusters very hard and continuously at some point in the orbit, and what that will do to slow the satellite down, and what that will do is cause the opposite side of the orbit to move in closer to the Earth. So the satellite falls inwards as well as the sort of the permanent falling it has while it's in orbit. So it actually develops a pronounced perigee, and if you keep doing this firing at the same position in the orbit every time, you can slowly cause the perigee to become lower and lower and lower down towards the Earth. When at some point that will then come low enough down that the orbit as a whole will start to shrink and then eventually spiral into the atmosphere and re-enter. You have to be very careful how you do it. It will take several weeks. And you have to make sure also that as well as using fuel to do this, you have enough fuel to avoid other satellites such as the ISS and so on. The other thing too is that whereas the satellite will normally be oriented to provide the minimum amount of light on the Earth's surface, the minimum reflection, you also have the issue that as you get further down, you actually want to maximize the amount of atmospheric drag. So you orient your satellite differently so that the Earth's atmosphere will drag on it more effectively. You slow down the reaction wheels, drain the batteries down, power it down. This is the very end stages before re-entry, so that when the satellite re-enters, it literally is a dead object re-entering and burning up. Again, this doesn't address what happens if the satellite becomes unresponsive, especially if it started the falling in process. How do you then avoid other satellites? It hasn't been a problem much so far with satellites, but of course there are going to be a lot of them, and it's not just a problem for SpaceX. It's going to be a problem for all of the Megaconstellation satellite operators. So one of my concerns is that, in particular, if SpaceX get permission to launch 42,000 satellites with a 5 to 7 year lifetime, it's a fairly simple process of division to say that you're going to have to deorbit between 500 and 700 satellites per month. And you're going to have to launch 500 to 700 satellites per month to replace them. This is one of the reasons why being able to launch 400 at a time on one of the Starship launchers is going to be a good idea. To launch 500 to 700 is going to take about 10 of the Falcon 9 launchers that he's currently using. So there's going to be pollution from the launch vehicles, pollution from the re-entry. You've got all of that electronics, much of which is going to use rare earth metals in the electronics. And you're launching them into space, and 5 years later, those rare earth metals, iridium and things like that, are just going to turn into vapor. And even though SpaceX have said that they will have zero impact on astronomy, this is Elon Musk said it will have zero impact on astronomy. And if it's not zero, they'll work on it to make sure that it is zero impact. That might be the case when the satellites are optimally oriented at their in-service orbit altitude, but it doesn't explain how they plan to reduce the brightness when the satellites are going to be lower down and on their way down from orbit, or just been launched and they're on their way up to their in-service orbit. So even if you said that you're only going to see the satellites for 50% of the time on the way up or down, that's still about 600 brightish satellites somewhere in the sky from SpaceX alone. Now, the process, I actually specifically asked this question of one of the SpaceX engineers, because I did wonder if they're going to have to keep rotating the satellite to make sure that it doesn't reflect light down to the ground. Does that mean they're going to be using the krypton thruster gas to a greater extent than they had originally planned? Because it wasn't originally the plan they would have this dynamic rotation of the satellite. This is a new thing. And they said, in fact, what they've got is something called a magnetotorquer on the satellite. This is effectively 3 large coils oriented at right angles to each other. And you pass an electric current through the coils, or one of the coils, and that electric current generates a magnetic field in the coil. And that magnetic field reacts against the Earth's own magnetic field to provide a twisting force on the satellite. So by careful use of electricity flowing through coils, you could actually rotate the satellite without using fuel. So magnetotorquers are a very clever idea for helping to keep the satellite pointing the right way. And not only the brightness of the satellites in the sky, but also, of course, if you're going to have 600 or so per month re-entering the Earth's atmosphere, that means that roughly every day, somewhere on Earth, there will be 20 streaks across the sky as these satellites re-enter. There is the Kessler syndrome. Many of you may have heard of the Kessler syndrome. It was popularized in the film Gravity with Sandra Bullock and George Clooney. Named after Donald Kessler, and it was a paper he and Berton Palais published in 1978, where they looked at the satellites that were being launched back then. And they came to the conclusion that the satellites, if by the year 2000, the number of satellites in orbit at the rate at which they were being launched could potentially collide and become a chain reaction, ending up with a ring of debris around the Earth. They predicted this would happen by the year 2000. It hasn't happened yet. But of course, putting up as many satellites as the Megaconstellations are proposing significantly increases the risk. Now, one of the saving graces of low Earth orbit is that any debris which is generated is more likely to re-enter because of atmospheric drag. So even if you had 2 satellites collide, you may get a spike of debris in orbit, and after a few years, that debris was probably going to re-enter. However, that still means there's a spike of debris and potentially access to space. Launching something up through that debris could be dangerous. It could be dangerous for existing satellites in orbit, and I wouldn't want to be on the ISS where there's debris going around. And I just think that over a few years, the amount of debris that could be there could cause problems before it falls back to Earth again, and maybe even enough damage that you do get another spike caused by secondary collisions. Even if it never actually progresses quite to the point of chain reaction of runaway that Kessler envisaged, it could still do a lot of damage. Okay, so now moving on to the radio astronomy side of it. These are the radio bands, and you can see here that the blue arrows here show the radio bands are used to transmit down to the Earth, and then you've got the green band here, which is used by the Earth to send signals up to the Starlink satellite. These 2 pink bands here are typically where the radio astronomers have protected use of the spectrum. And Starlink the SpaceX have said that here, where you've got these 2 adjacent to each other, they won't use the 10% or so of that blue arrow that's right next to the radio astronomy band. Even with the best designed antennae, you do get side lobes where the signal leaks sideways to a certain extent. And also, even with the best designed transmitter electronics, you will get side bands where some of the energy leaks into frequencies either side of the intended frequency. And so even using this band here with a gap, you may still get some leakage across to the radio astronomy spectrum. Added to which, of course, radio astronomy has reserved some specific frequencies for its use, but that sort of expects that all of the radio sources that you're looking at are stationary relative to you, which of course is not the case. Many of the radio sources are redshifted to a low frequency. And not only that, so that means, for example, that they are going to be they're going to be sending their signal, the galaxy sending its signal to you at a frequency other than, for example, the typical wavelength for hydrogen. Not just that, but of course, if you're doing some types of radio astronomy or submillimeter astronomy, you're looking at other molecules. You're looking at water or hydroxyl or radical or the cyanide. And those particular bands aren't reserved, they're not protected. So there are some frequency bands where reserving a band isn't an answer. You also have around some of the bigger radio telescopes something called a radio quiet zone. The square kilometer array, for example, has a radio quiet zone where you're not allowed to have walkie-talkies or other types of transmitter within so many miles of the radio telescopes, because interference will damage the work. Elon Musk or SpaceX have said that they will arrange to steer their beams around the radio quiet zones. And that's all very well and good, of course, for the big radio astronomy observatories, but it doesn't help if you have a smaller observatory or if you're an amateur radio astronomer, because they're not going to steer their beams away from your setup in your back garden, for example. So it's not a perfect solution. The other problem is that even if your Starlink satellite were to turn off all of its transmission or to beam its transmission somewhere else, it turns out that many of these larger radio observatories are sensitive enough that they can detect the electronic noise from the electronics on the satellite itself. Unintended emissions, if you like, from the satellite can be picked up. The other thing is, if this goes wrong, if something goes wrong and the beam happens to cross your radio telescope, the consequences for the electronic equipment that are picking up now a very powerful signal over a large area on the ground and focusing it all into your radio receiving equipment means that very often you will damage that radio receiving equipment by the sudden, very powerful signal. As somebody once likened it to trying to look at a 10th magnitude star and then somebody turns a floodlight on. So a little bit first now about the geometry of the visibility. This is about the illumination side of it. We show here at the top half the sun 15 degrees below the horizon. We've got a satellite here at 1,000 kilometers altitude, and this is drawn roughly to scale apart from the observatory. And most professional astronomers say that they tend not to observe much below 30 degrees elevation, 60 degrees zenith angle. So you can see here that any satellites that are orbiting here will be visible because they will be illuminated by sunlight. Also, any satellites in this area, because of the angle that they're at, stand a much greater chance of glinting reflections from the sun off the satellite and into the observer's eye. So below 30 degrees, you'll probably see the satellites more brightly. And as I say, you may get glinting reflections off the solar panels. And this is part of what SpaceX want to do in orienting the satellites to try and reduce glinting and unwanted reflections. Once the sun goes further down, in the lower diagram here, you can see the sun's 30 degrees below the horizon. You can see that this part of the arc is now unilluminated, and so satellites will not reflect the sunlight there, and you won't see them, even though they're still there. So the radio astronomers and the infrared astronomers may still detect them even in the dark part here. So that has to be borne in mind, of course, and it has implications as well as to the time of year that you're looking, because at certain times of year the sun will be further below the horizon than at others. I put this diagram into my FAS newsletter, and in retrospect, it maybe is a little of teaching granny to suck eggs here, but you can see here this is set up for the latitude of Birmingham, and you can see that here below the northern horizon, you can see that down here in the winter time, the sun is 60.9 degrees below the horizon, whereas in the summertime, the sun here is only 14.1 degrees below the horizon. So that has implications for how much illumination there is. And the next diagram here shows the satellites at different altitudes, what percentage of satellites are likely to be illuminated. Effectively, how much of that dome within the 60-degree zenith angle, how much of that curved dome the orbit could be in is illuminated. So you can see that for satellites that are down here at 290 kilometers, this is the initial injection orbit where they're tested out, you can see that they, as the sun here, the sun setting down this direction, very quickly these satellites fade from view, and you're down to 40% with the sun being at 18 degrees below the horizon. Whereas if you have the satellites higher up, so moving vertically upwards in this graph, satellites at 340 kilometers, 60% still visible. And moving further up here, satellites at 550 kilometers, 90% of them are still visible when the sun is 18 degrees below the horizon. And if you've got satellites out at 1,110, that's up here, all of them are still visible. One of the worries is that one of the changes that OneWeb has talked about for their satellites is not launching them into 1,200 kilometers orbits, but 8,500 kilometer orbits, where of course they will be pretty much visible all night. So that's not good. And that's one of the things we hope to change their mind on. So we've talked about how many there are. We've talked about their visibility in terms of illumination. But of course, there is the issue of how bright they actually will appear. And that will depend on what faces of the satellite face towards you, and because they've got multiple facets, different brightnesses of the actual surface, different reflectances. It depends on also the sun satellite observer angle. And so far, some of the estimates, this is the pre-visor sat estimates, were that at 550 kilometers, they will be slightly brighter than 6th magnitude. With the visor sat, some of the early reports are that the brightness is about or slightly fainter than 7th magnitude. That's not really faint enough. So most professional astronomers would want it to be rather fainter than that. And I think also for those astro imagers, 7th magnitude satellite passing through their field of view would still be recorded. However, they are much brighter, of course, during the orbit raising and deorbiting phases, where some of them have been seen as bright as 1st magnitude, and sometimes to a more commonly 2nd and 3rd magnitude. And this is also one of the reasons why SpaceX are working hard to try and come up with a good algorithm for how they rotate the satellites dynamically to try and avoid reflections down to the ground, and why they've put the visor on so that the visor will shade the underside of the satellite so that it's not as bright. Excuse me, just take a sip. in the early stages, they did take one of the satellites, Starlink 1130, and they did paint it black on the underside, but it only produced a reduction in brightness of between 0.8 and 1 magnitude, which isn't enough. And it also started to cause them problems with the temperature of the satellite. If the satellite is black, it doesn't radiate as well, it absorbs the sunlight better, and therefore the satellites were overheating, which has implications for their lifetime. They're running at a higher temperature. So I think they've abandoned the idea of the dark sat in favor of the visor sat, and in fact they have said that all of the satellites that they're going to launch from now onwards will be visor sats. So I produced this table. I've taken out the 1,200 altitude orbit that was in my FAS newsletter article. I did write to SpaceX and said to them, look, if you're going to maintain 1,200 kilometers, my table won't fit on my slide. So they've very kindly reduced all the orbits down to these three principally, and thereabouts. So you can see from this, first of all, at a particular elevation. So if you're looking, say, 60 degrees up, of course, the lower down, nearer the horizon you look, a satellite in a given altitude of orbit will be further away. So if we're looking to say here at 60 degrees, a 550 kilometer altitude satellite will be 627 kilometers away, because you're looking obliquely out through to it. From the distance, you can also then say, well, typically what will the approximate size be, about 3 arc seconds. And also you can make estimates of the velocity. Now, this is taking, first of all, the first number is if the orbit is such that you're looking at the satellite going at right angles to your line of sight. So perhaps you're looking down towards the apex of the orbit from somewhere up in Edinburgh, say, where the satellite is going to be traveling from west to east. Then this would be the number of arc minutes per second. If on the other hand you're a little further south and the satellite is traveling straight towards you and up and over your head, then this velocity here is the velocity at the zenith. So it gives you a kind of a range of velocities in arc minutes per second travel across the sky. And so you can then move to a fairly sort of back of the envelope type calculation, where you can get the satellite density in the sky, and you get that from the graph I did earlier on, a number of satellites per 100 square degrees. You've got here the field of view of the telescope or binoculars, and here the time of exposure for if you're taking a photograph through a telescope, and here this is the angular velocity in arc minutes per second. Divided it by 60 to give you the field, giving you in degrees per second. So for, say, a typical amateur telescope here with a 1 degree field of view, that means that there is approximately a chance that within the space of a 5-minute exposure, I think it is. How long have I said now? I should put that on the slide, shouldn't I? I think my original. Yeah, sorry, it's for a 10-minute exposure. So this is for a 10-minute exposure, means that within the space of 10 minutes, you stand approximately a 3 in 4 chance of getting a satellite across your field of view. If you're using something like the Vera Rubin telescope, which is what used to be known as the Large Sky Survey telescope, because of its very wide field of view, you're likely to get up to 7 satellites pass through the field of view in the same period of time. So it's a problem. There is going to be a significant number of images that will get ruined by satellites passing through. Luckily, as astronomers, you could argue that the work is not critical in the sense that it's only your free time that's being wasted. But for professional astronomers, of course, it's difficult. You've got satellite telescopes booked months in advance. You've only got a certain amount of time to make your observations, and these satellites could completely ruin your slot for observing. With something like the Vera Rubin telescope, which takes two pictures typically about 15 seconds apart, they're saying that the number of satellites will there'll be about one satellite per every 6 exposures, and that's a serious problem for them because, of course, it's so big. Because again, they've got such a wide field of view. Okay, I'm going to come back to talk about the Vera Rubin telescope in a minute. I'm sorry, I'm running over again. I'm just going to change where my screen share goes to share a different thing. This is an application that I wrote. It's still very much in the development stage. It takes a couple of seconds to load because there's some biggish files there. Can everyone see at the moment? It's mostly a black screen.
Yes.
Okay, thanks. I can only see Jim at the moment. Everybody else has muted their video. Good, thank you. So we can see here the Earth against the starry backdrop. This address, I'll go back to the slide afterwards, anybody can get to, and as I update it and add to it, you'll be able to see the update improvements as I do it. So we've got here the Earth, and I can use the keys on my keyboard here to zoom into the Earth, and I can even move my position. So if I now turn on the phase 1 and phase 2 satellites, this is the number of satellites. I've made the size of the satellites adjustable at the moment. I mean, you can have them very big, it just makes no sense at all because it doesn't look quite that bad. So if I get a figure about there somewhere, can you see the number of satellites in the phase 1? So this is the first 12,000 SpaceX satellites, and you can see there they're orbiting, traveling up in an arc to this 53-degree area and down again, but there are others and more inclined orbits further up. If I zoom further in, you can see here what I mean by there appearing to be a concentration of satellites above the 53-degree area. This is running at faster than real time at the moment. If I slow it down a little bit, that's more like it. You can still see the satellites moving, but that's nearer real-time movement. If I turn on the other 30,000 that they want to launch, that makes it even more obvious. And you can also see quite clearly here that the phase 3 satellites are clearly their boundary is lower down than the phase 1 and 2 satellites. So you can see there a considerable number of satellites passing over the UK at any one time. I'm aiming to improve performance on this. I should be able to get it back up to 30 frames a second if I'm a bit more savvy about how I do it. And I'm also hoping to take the SpaceX satellites and replace them with proper looking satellites as opposed to what I've currently got, which is representative spheres. So currently there, I'm modelling the position of 42,000 satellites, and I should be able to get up to over 100,000, adding in OneWeb and others as well later. But as I say, it's a work in progress. Okay, let's go back to my original. So this is the web address. That's my own server. I also want to do something like the ability to tie the camera to the ground, looking up. So that's because the Earth rotates then in that simulation. To tie the camera to a point on the ground at some chosen latitude, so you can actually then turn around and look up and see how many satellites are passing through a certain field of view. Okay, moving on. Lost my apparently up. Good. Okay. I apologise, finger troubles here. I'll just close my presentation down. Nearly there. Shares again. You got the slides back again? I'm looking at Jim. Okay.
Yeah, they're back.
Okay, thanks. So this is a picture that was taken, or I say a simulation taken of what it would look like for a picture taken through the Vera Rubin telescope. Because the Vera Rubin and other large telescopes will use CCD sensors, they are very, very sensitive, but they do suffer from problems of saturation and artifacts. So here we've got a simulation of what a satellite track would look through and what the artifacts would look like. And in fact, they did say that maybe if you could reduce the brightness of satellites down to about 7th magnitude or below, fainter, then you might be able to post-process some of these pictures. Reducing the saturation will reduce the side effects. These here are ghosts of the saturated track, and they're difficult to remove. But also because you've completely saturated the track here, it means that anything under there is completely unrecoverable. So if you have a star under there or a galaxy under there, there's no way that you can post-process to remove the saturation. So the aim here is to try and at least mitigate it by reducing the brightness. I say here mitigate, it doesn't solve the problem. So I think, like many of you, there's still a sense of outrage. Why should we even have to be doing this to post-process the data from a multi-billion-pound telescope that hasn't even seen first light yet? It seems somewhat crazy. How did the FCC get permission to provide a license for this? So this is here a cross section of some of the orbits, and you can see here this is the Earth with the curvature here to scale. and you've got here the initial batch of phase 1 and 2, so phase 1 satellites here at the 540, 50, 60 and 70 kilometer orbits, which is the red, orange and purple and blue here. Now, it turns out that the Hubble Space Telescope orbits between these two dotted lines, which means that potentially the Hubble Space Telescope is going to be at a similar sort of altitude as the lowest of the those phase 1 satellites. I think it's likely, of course, that they will organize it so that the Hubble Space Telescope isn't going to collide. But of course, if there is any collision between satellites in orbit and you're going to get debris, then the Hubble Space Telescope maybe could be in line for getting some of the debris. Added to which, when I showed my little demonstration earlier and you were looking sideways through those satellites, those orbiting satellites, there was a much more obvious concentration of satellites along the line of sight. And so the Hubble Space Telescope, orbiting here, just below the lowest of these, will be looking at through all 4 of these shells of orbits. And so there potentially could be a lot of satellites passing through the Hubble Space Telescope's field of view. Not only passing through the field of view, but it could be that at times the solar panels will be pointing back towards the Hubble Space Telescope. If the satellite, as seen from the HST, is in the anti-sun direction, you potentially have the ability for a satellite to have a very bright glint back towards the HST. And I don't know what damage that might do to the HST sensors. Permanent damage, perhaps. There are other satellites too. ESA has Cheops, which is in a sun-synchronous orbit. So its orbit stays oriented relative to the sun all the time. So it keeps the sun, describe with that drawing diagrams. It's a sun-synchronous orbit, and it has a 60-degree field, 60-degree range of viewing away from the anti-sun point. Which means that it could also, at 700 kilometers, it's not that far above 570, it could still pick up some of the satellites in the extremis of its Earth side of its field of view. The NASA's WISE satellite is at 525 kilometers, which is lower than these, at 97.5 degrees inclination. So it's got a field of view of 47 minutes, but it's going to be, again, potentially looking out through all of these satellites. So in summary, for the professionals, satellites don't have to be illuminated to cause a problem. For the radio and the infrared astronomers, they're a problem. They emit their own electronic noise of their own, and beam steering may not be enough to solve the problem, and certainly not for all of the radio astronomers. You've got parts of the bands that are now going to be occupied by lots and lots of Starlink satellites, and maybe can't avoid them. And of course, I referred to it earlier, the infrared means that there's thermal lag on the satellites that may be visible even when they're in the shadow. For amateurs, you've got generally smaller equipment, and so you haven't got the wide fields of view that most of the wide field cameras have got. So smaller field of view and probably less light gathering power means that you're not so likely to see them. Many amateurs, of course, also don't mind too much if there's the occasional satellite, and they see them visually with the naked eye as a point of light, not a streak across an image. The people who are most going to be affected are going to be the amateurs who take long exposure photographs, deep space photography, deep sky photography. But then again, most of the cameras, DSLRs, will use a CMOS sensor, which is cheaper and less, more noisy, but less sensitive than a CCD camera. But it may be possible, therefore, for some post-processing to remove the trails. And of course, amateurs also have easy access to software, to stacking software, to throw away images that are impossible to use. Obviously, some amateurs will use a CCD sensor, the rich ones, and you're going to find it a little bit harder to remove trails, perhaps in those cases. There are going to be software apps made available for your phone and your tablets and your PCs to help you predict when these satellites will come over. SpaceX will have to keep that database active and up to date and accurate. And it may well be, of course, that you can then come into hardware solutions or software solutions where you perhaps have a shutter in front of the camera that will close when a satellite is about to pass through the field of view. Or maybe you have a way of just disabling the sensor temporarily so that it doesn't capture light while the satellite is passing overhead, passing through your field of view. So for the public, most of the public who aren't aware of the general threat to astronomy will still see this as something of a curiosity, as a spectacle. And you've seen a lot of your local newspapers reporting these spectacular shows of satellites and a bit like a celestial fireworks show. I think to begin with, they weren't fully aware of the threat it means to astronomy, and they aren't aware of the threat for the use of space in general. And you can see also that there is now starting to appear more and more awareness in the media of the number of satellites that will be up there, but more particularly of the potential damage caused by space debris. Even if you are able to reduce the satellites to be below naked eye brightness when they're in service, as I've said, on the way up and on the way down, they may well be brighter. So that may not be a complete loss of all of these satellites, even if SpaceX are able to make them invisible higher up. And one of my concerns is that something that really inspires you is being able to lay out under the stars at night and see a relatively pristine sky. Okay, we've got the occasional aircraft and sadly clouds, but what if you've got a lot of satellites there, making it much harder to enjoy the sky? And maybe there is a reduced inspiration for youngsters in particular, and maybe that will affect the number of them that go on to become scientists. So I've got just 4 slides left. Very quickly as a wind up. There's always 2 sides to the story. The Starlink satellites are going to be launched to provide global internet. The idea is that you could have the Sahara Desert with satellites going over it. You're miles from a transmitter anywhere, but you can still get internet via the Starlink satellite network. So in an increasingly digital world, some people will place rather more emphasis on global internet access rather than astronomy, particularly if you happen to live in an area where there is very, very poor internet connection or no internet connection at all. There are no global laws that control the way that satellites are launched. There was the Outer Space Treaty in 1967, extended later, 63 signatories, including the US, the UK, and Russia. This is a treaty that was put in place very early on. If you think back, that's only 6 years or so after Sputnik. And the principal reason for it was that straight away there was realization that you could launch nuclear satellites into orbit and have them drop out of the sky on your enemy. And so straight away, the Outer Space Treaty came into place to stop the use of space for weapons of mass destruction. It also said that no one can own space. You can't own orbits. You can't own the moon. So even planting a flag on the moon doesn't mean you own it, or planting a flag on Mars won't mean that you own it. You can't claim Mars for the United States. And one group of countries around the equator tried to claim slots in the geosynchronous orbit that were over their territory, effectively projecting their east and westmost boundaries of their country up and onto the orbit and saying, right, that bit of slot in that range is ours. Anybody else who uses it's going to have to pay a license and so on. And in a sense, what they were thinking was that eye to the future, if we become a developed country and we want to put our own satellites up, we want them over our own country, and we want to make sure that nobody else can completely use up our slot. There were 7 countries, including Brazil, making 8, and the meetings were held in Bogota in Brazil, which is why it's called the Bogota Agreement. They came up with a declaration that these slots were theirs, and everybody ignored it, which was somewhat prescient when eventually the United Nations came along and said, we want to pull back control to us on where orbits are allocated. What do you do if you want to go to the moon or to Mars? So effectively, outer space activity would fall under United Nations jurisdiction. By 1979, however, spacefaring nations had rather woken up to the potential for being in space. It didn't stop them putting military stuff into space, just not weapons of mass destruction, but there was the commercial attraction of space. And so even though the United Nations tried to get the Moon Treaty going, there were no major signatories, certainly not the US or the UK or even the European Space Agency by then, and it's been widely ignored. In 2015, Obama signed an act which effectively said that US companies could own and sell resources extracted from the moon, asteroids and other bodies. Not that you could own the moon or asteroids, etc., but if you brought back lumps of moon rock, then they belonged to you and not to humanity. So the Outer Space Treaty already is being nibbled away at the edges. It is trying to say that outer space is a global commons, meaning it belongs to everyone. And already, if you're saying that some of the material from up there, if you bring it back, it no longer belongs to everyone, it belongs to us. You could argue that's reasonable if you put the money and the investment into going to tame a pet asteroid and bring it into Earth orbit or something. You could argue, well, yes, it should belong to you. But yeah, it's still nibbling away at the edges. Then along came Donald Trump. In April this year, he signed an executive order saying that as a right, private companies could claim and recover resources in space. But it contained this rather chilling phrase, outer space is a legally and physically unique domain of human activity, and the United States does not view it as a global commons. So that phrase suggests that if they go to Mars, they will want to claim Mars. It's assuming Trump's still in power then. I'll skip over slightly over these 2 bits here to do with this, but basically there is potentially some challenge possible against the FCC for not observing the necessary environmental acts, but more particularly they're supposed to keep their rules and regulations on what's a sensible launch up to date, and they haven't done that for 30 years. So it may be possible to get the FCC to reduce the satellites that can be launched, not to approve the 30,000 until they have updated their policies on satellite launches. So maybe we can put a spanner in the works of the other 30,000 using this second situation here. Okay, so SpaceX are already getting military contracts. For example, using the refueling tankers that fly around and where the jet fighters come and connect to the nozzles trailing behind them. They're trying to use or set up tests to use Starlink satellites for helping to guide the jet fighters into position behind the tankers. They're talking about using Starlink satellites that do pass over the pole to provide battlefield management control in the Arctic regions in particular, where, as I say, there is little other coverage. Talking about maybe using cruise missiles able to be controlled by internet connections via Starlink. And as part of this recognition by the US military, Trump, December last year, created the US Space Force, so a 4th armed service as the US Space Force. And here, I mean, they are there to protect US and allied interests in space. So that's when you look at his previous his April edict of we don't consider space a global commons, in line with setting up a space force to protect US interests, means that maybe if there are US launched satellites in space and someone decides to take a pot shot at them, then it may be that the USSF, the Space Force, will consider that to be an act of aggression and have the authority of the president to retaliate. There's another document I wanted to show you very quickly here. This is my last but one slide on there. If I just stop and share this with you. This is a document that was produced, I think it was February 1979. This is Vision 2020. There you see that. So that's the start of it. Vision for 2020. And produced by the United States Space Command, as it was called back then, signed by various commanders-in-chief and generals and so on, and even including this rather interesting Star Wars type lettering down here at the bottom, and lots of diagrams and the evolution of space. So they're setting here an agenda for the American military to have much more of a presence in space. Information superiority relies heavily upon space capability. Space systems will be targets. Control of space capability. You can see here that the language is very much directed at the US control and domination of space in a military sense, if not a commercial sense. It is slightly worrying. And I know the bright colors and everything else suggest that it's more like a PR pamphlet from Ming the Merciless. But this should worry you, because this is a hint to what the Americans thought back in 1979 should be the US role in space. So, my final slide here, we have the US attempting to dominate the use of space. And that is potentially a problem, because you've got other countries also trying to make use of space. You're going to get megaconstellations from other countries, companies in other countries. The Chinese, the Russians, the Indians will all want their satellite systems up there. So the 42,000 that SpaceX want to put up there is only the start of it. And you have, therefore, a greater need than ever to get international treaties in place. But we had a little bit of a forewarning on that from the Moon Treaty that was ignored by all the major spacefaring nations. Why would you sign up to something that's cutting off your nose to spite your face? In the same way, if you do come up with international treaties with the best will in the world, they're trying to do that now again in the United Nations to deal with this mega constellation problem. Why would the Americans sign up to it, given that they're going to make so much money from it? And the military have got their fingers now deeply embedded in the pie. And once SpaceX gets thousands of subscribers using their service, it gets much harder to back away from having this Starlink style mega constellation. What happens if the Russians decide they don't want these satellites passing over their borders? They've gone to great lengths, as have the Chinese and Iran, to put digital firewalls around their countries so that they can control what their citizens see and who they can communicate with, and they can monitor what's going on. if all of a sudden there is the potential to communicate with an American Starlink satellite going overhead, providing connection to the global internet, all of a sudden the Russian government have lost control over what gets into or out of the country, and the same for the Chinese and Iran and so on. So that represents a threat to their sovereignty as to what they control, what their people can see. My final point, if you remember back to the UK general election, December last year, do you remember Jeremy Corbyn saying, we will nationalise broadband so that the government will be responsible for providing broadband around the country. And on the face of it, that might sound like a good idea because you've got the government investing on a single unified network for broadband. But of course, it also means that the government would have the potential to control that internet within the UK. What if the US government is able to impose sanctions on a country by telling SpaceX to turn off their transmitters over that country, effectively imposing a digital sanction on the country as well as goods and other types of trade? So you can see that the threat is not just to what you see and what you photograph. The threat is also to space debris, and not only things like collisions in space and the damage it might do to satellites we put up there for scientific and research purposes, but also maybe the difficulty of simply trying to find a launch window to launch something up through these shells of satellite orbits. And then you've got the legal and international ramifications as well. Thank you very much.
Okay. Alan, or do you? Alan, you're muted. I'll unmute you.